There is a lie about the double slit experiment that's told by everyone from famous physicists to YouTubers and even ways to believe it. The lie is, hen you shoot electrons at two slits, if you don't watch which way they go, cruff, they'll act like waves. But if, you do watch which way they went, then, hey, act like particles. They go, straight through, and they end up in two-bar lumps. This actually contradicts the salts of the experiment, and it's completely the wrong lesson to take from he double-slit experiment. But this Lieber has been told so often that it's kind of a life of its own. The real lesson, F this experiment is way more interesting. And I want to tell you about that. But first, let's find out what the electrons actually do when you serve them. Because it's not this Magina. We do have a bunch of articles like this that are going to craft this double slit experiment. You expect to have like two bunches of articles. And actually these slits are airy, narrow, and very close together. So, you'd kind of expect a bit of overlap between those two heaps. But here's what old happened for a wave. Okay, so I love his website because it's a wave emulator, and I'll link it in the description. But basically what we're owing here is we have this wall with two arrow slits, and we're going to see what happens when these waves go rough. So what you're seeing happen here is that there are these two A's coming from each of the slits. But when they touch each other, something weird happens. They interact with each other and kind of overlap. And if we let this go further, these interference patterns always kind of look like this, where there's a very strong bit of wave in the middle, and there's not much, and then there's more wave, and then again, there's a blank spot, and then another strong spot, etc. And as we saw in that simulation, what you'd expect for a wave is that it hits this back wall in this very funny pattern. There are some spots like this one where it's very intense, and then there are some spots like this where not intense at all. And there are these little bands of, intensity and no intensity. And when you do this experiment with light, that's exactly what you see, which suggests very strongly that light is a wave. In fact, the double slit experiment was the thing that really convinced people that light is a wave after all. And I've done the double slit experiment in a couple of videos before, and I always get a lot of comments being like, this is just classical optics, and that is true. But then they say, therefore, it's irrelevant to quantum mechanics, and that I disagree with, and I'll explain why a little bit later. But first, let's think about the same experiment with electrons. Is it going to turn out more like the particle case or more like the wave one? Well, this is footage from an actual double slit experiment using electrons. So let's see what the answer is. Well, it's looking very promising for particles, because unlike with a wave, the result isn't just sort of smeared out. It's coming in these individual dots. But if we let the pattern develop, you start to see that it actually isn't in two lumps. It looks much more like the double slit interference pattern for waves. So something really odd seems to be happening with these electrons. There seems to be some sort of wave associated with the electrons, and the wave spreads out. And just like a water wave or a light wave, it goes through both slits. The only real difference between an electron and a wave that goes through both slits is that the electron still ends up as dots. It isn't smeared out the way that waves usually are. But this feels wrong, because for something like light, it's perfectly fine to accept that it's some sort of wave. But for electrons, we're used to thinking of them as little bullets like this, little particles. And a particle couldn't be going through both of these slits at the same time. That's why it's really natural to think that if electrons really are going through both slits, then maybe let's try and catch them in the act. Let's put two measuring devices here and here that will watch both of these slits, and we'll tell you whether the electron actually goes through both slits. The idea is that we want to be able to catch the electrons doing both things at the same time, but measurement in quantum mechanics doesn't work like that. So in quantum mechanics, when you try and measure an object, that's in a superposition of two different things like this electron going through both slits, then you will see a particular result. For example, this detector might see an electron go by. But now in quantum mechanics, what happens is that measurement changed the electron. Now it's only going through one of these slits, the one you observed. So far this is all correct. But here comes the myth. Many people will tell you that now that the electron has been measured, it becomes a particle. And so this particle will act like any normal particle, will sort of end up here. And so you can imagine that if we keep measuring which way every electron goes, then you end up with two piles of electrons. People will draw the results just like this as two clumps, or at most as two overlapping clumps. And so before I ever did these experiments myself, I assumed that this is what happens, but that's not at all the case. And I'll get a curve that will probably look more or less like this. I wish I had experimental footage of someone actually doing this experiment with electrons to show you that this is not what happens, but I don't. And I also can't do this experiment myself because working with the electrons is really hard. You need like a vacuum pump and everything, but the results that you get when you do the experiment with light are very, very similar. And so I did that experiment in my previous video, and this is the result that I got. What on here? Is this crazy pattern? It doesn't look anything like two lumps. This is actually called the single slit interference pattern, and it's still very much wave behavior. Let me show you. So this is what the interference pattern looked like with the two slits here and here. But what happens if we take that away and instead just have one slit? So here I can change this from double slit to single slit. Let's see what happens. Okay, so it's much less distinct now, but you can still see some funny pattern going on here. So look, what happens at this bit where the slit is, you can see that there's like a funny sort of edge effect on both sides, and that edge, these two edges are what are going to interfere with each other. So the edges of that single slit interfere so that you get this kind of weird interference pattern. It looks quite similar to the double slit one, but just with like less fringes. So there's this bright fringe and then dark fringe and then a much less bright fringe and a dark fringe, etc. The single slit interference pattern looks something like this. But again, when we do this experiment with electrons, not actual waves, what we get is a slightly different pattern. We still get the electrons arriving in individual dots like this, but it's just that the dots are going to be according to this pattern. If you're wondering how this is different from the double slit experiment, remember that there were all these little dips inside of the bigger single slit pattern like this. So when you're not observing and you let the electrons go through both slits, then you get even more interference. But even when you just allow the electron to go through one slit by observing it, you still get a wave interference pattern. So what's going on? Well, let me tell you the correct explanation of the double slit experiment according to quantum mechanics. So for both light and for electrons, there is this thing called the wave function, which I've drawn here. It's the wave associated with that object. And when the two slits are open and not observed, the wave will go through both of those slits and interfere with itself. But in quantum mechanics, if you ever try and observe the position of an object, it can no longer be spread out like this. So when you do this observation, it forces the electron to collapse to just one of these. And so the electron acts like a wave even after it's been observed. And we know that because you end up with this single slit interference, which is just impossible to explain with purely particle behavior. If it's a wave, then shouldn't we expect a big smear across this wall rather than these individual particle-like things? Well, again, our measurement rule comes into play. In quantum mechanics, you can have an object that is spread out like a wave, but when you measure the position of that object, it's forced to collapse to a smaller position. So we have an electron that goes through here. When we measure it at the wall, it has to choose where to turn up, and it's going to be more likely to turn up in one of these bigger regions. So are electrons waves or particles? I think that even in this case where you're measuring the electron, it clearly acts in a way that's governed by this wave function. The wave is what determines what it does. But there is a sense in which it's particle-like. And that is because when it turns up on the wall, you find that there's always a full electron that turns up in any one spot. Like this electron has the same mass as that electron. So the fact that they arrive as these discrete and countable and always sort of the same size packages is what makes them particle-like. It's the fact that they can kind of be counted. And here's where it gets a bit weird. Light is exactly the same. In my previous videos about the double slit experiment with light, I got a lot of comments saying that the experiment that I was doing was just an experiment from classical optics, and all it showed is that light is a wave, which we've known for a long time. And that is all true, but I think that the quantum version of that experiment is not what people think. I got a lot of comments saying, why don't you do the single photon at a time version of this experiment? And the thing is, I would love to do that experiment, but I actually think it's going to be a little bit underwhelming, because basically this is how you would do it. Say that this is my source for the light. Then to do the single P photon at a time version of this experiment, all I need to do is to turn down this light. So I've just maybe put some filters in here that block the majority of the light. So there's only a little bit going through. Now our intuition tells us that if light is a particle, this thing called a photon, then surely it needs to be a particle like those little bullets that we were talking about. In that case, it would make total sense to talk about a single photon going through this experiment at a time. But that's not how light works. If I just put a filter in front of this laser, all I'm going to do is I'm going to make this wave weaker. From the side on view, the wave would look something like this, right? And as you put more filters in front, all that will happen is that the wave will get smaller and smaller. But no matter how many filters you put here, it's still a wave. At no point does it become a particle like this. And so you can see that no matter how weak these waves become, that doesn't stop them from spreading out like this. And the spreading is what really causes the double slit interference pattern. And so you still get the interference pattern. However, there is one really different thing about the result. Instead of getting a smear like you usually do with a double slit experiment, you're going to find actually the light arrives in little dots just like the electrons. But how is that possible? I said that nothing really changed when you turn down the intensity of this light. Well, the thing is, when we have this light at full brightness, there are individual dots turning up here, but we can't see them because there's so many coming per second that it does just look like a smear. And it's only by turning down the light that we end up seeing these individual photons. So photons are particles much like electrons are particles. They're not really, they're more waves. But a photon or an electron is more a property of what happens when they get measured. Whenever you have a quantum wave function like this and you try and measure the position of that object, it's forced to collapse to one particular spot. After I finished recording, I found out that there's this amazing paper where they explain how you can see the individual photons of light arriving. It is from 2016, and I'll link this in the description, but here's the video. So as you can see here, there are these individual photons, and it kind of looks random at first, but you can already start to see how it seems to be gathering around these fringes, which is exactly what you would expect for a double slit experiment. I'd seen this experiment with electrons before, but it was very cool to see it with photons. And as you can see, the two experiments look nearly identical. Another way that photons are very like electrons is that each individual photon has the same amount of energy as the other. Just like with electrons, they come in these discrete packages that are always of the same size. So for both electrons and photons, they don't really exist as particles. Throughout this part of the experiment, they only really become particles here when they're measured. But then you might wonder, how can we even talk about doing this experiment one photon at a time? Well, the way that you do it is you kind of turn down this light a whole lot so that there's only a few of these photons coming, let's say, every second. And it takes much less than a second for any light to have gone from the source all the way to the wall. And so you kind of say, well, that means that there couldn't have been more than one photon sort of going through this whole thing at a time. So that's a one photon at a time experiment. And I think that just is bad terminology. Like, there are no photons, really, until you get to here. For both electrons and photons, we imagine these as sort of individual balls coming out of the source. And that's what's the source of the confusion, because we think that a single particle can't go through two slits at the same time. But there is no contradiction when you see that both of them are actually just waves. And waves absolutely can go through both slits at the same time. They really only become particles when they're measured at the wall. That's why I think that experiments with light are still very interesting quantum mechanically, because we know from the maths of quantum mechanics that light and electrons behave almost identically. Like in my last video where I did the quantum eraser experiment with light, and it was very easy, and it just involved polarizers. A lot of people pointed out that you can totally explain this just using the regular polarization of light in classical optics. But did you know that you could do that exact same experiment again using the spin of the...
On a routine flight between Helsinki and Tartu, a pilot glanced at his navigation instruments and felt a sudden cold wave of disbelief wash over him. The plane, which should have been coasting over the Baltic Sea, was inexplicably thousands of miles off course, hovering above a remote stretch of the Pacific Ocean on the opposite side of the world. Now this sounds like the opening to Lost. The reality is something much more scary. Russians, specifically a concerted body of activity to disrupt the way we navigate around our planet using the Global Navigation Satellite System, or GNSS, to provide GPS data. In fact, we can actually see this happening. This is the global survey activity that measures GPS threats and interference around the world. As we pan east, we notice a significant increase in the failure rate of GPS fidelity, with particularly high compromise exactly on the Helsinki-Tartu flight path. By assuming the line of sight is needed for this GPS attack, and looking at the signal strength in the area, internet sleuths narrowed down the likely source of this phenomena to just west of St. Petersburg. There's also another interesting dead zone, but that one's located in the USA just west of San Antonio. What initially got me interested in this story was videos like this one that had been circulating the internet for a while now, and show in the middle of a drone show hundreds of drones suddenly falling out of the sky. There was an internet rabbit hole that I went down, that other drone companies were using GPS jammers to sabotage their competition. But all this brings me to one point in a world where our main means of navigation, both military and civilian, is so easily compromised. What do we do about it? I wanted to find out. So I reached out to a team of quantum physicists and engineers based in Oxford that are working on a solution, the world's first quantum positioning system that taps into the very nature of quantum mechanics in order to navigate. We hear a lot online, and you guys leave me a lot of comments that of quantum, much like fusion always seems 30 years away. This is a direct counterpoint to that argument. The magic behind their technique comes from the ability to control ultra-cold states of matter at inflection. We're experts in cooling and trapping atoms and manipulating them using magnetic fields and light. And the reason that we do that is that if you cool down atoms exquisitely cold, few billionths of a degree above absolute zero, then you can create a new state of matter. It's called a Bose-Einstein condensate. What inflection are trying to do is develop a new approach to position sensing. But what exactly does that mean? When we think about working out where we are on the planet, there are really two main ways of doing this. Either trilateration, which is used by GPS systems, where we have a constellation of GPS satellites in orbit, constantly sending out their position in the sky and the time on their local clocks. These radio signals travel outward at the speed of light from each satellite, and if you detect a GPS signal, you can look at your current time, subtract the time of the GPS signal, and this tells you how long it took for that GPS signal to arrive to you as all light. Waves move at the speed of light. The speed of light multiplied by this time difference tells you how far away the Satellite is from you, you now know the. Distance, you just don't know the direction to this satellite. But if you can do this for 3 or more satellites, you can get a ring of overlapping possible positions that converges on a single point in the planet telling you where you are, but actually GPS can be very easily spoofed and can be very easily jammed. So what I mean by jammed is it can happen for natural reasons. I'm in between large buildings, or I'm in a mountainous region, or maybe I'm under the ground, right? I'm on the tube. Trave. Ling around London, I'm not going to. Get a GPS signal. GPS can also be jammed with very cheap jammers that literally block the GPS signal. Spoofed is a little bit more insidious, where you look at your GPS signal. It tells you that you're in one place, you're really in another. That can be either in the theater of war, or like a few delivery drivers did a few years ago to disguise the fact they were taking naps throughout the day. If that is the case, then all of these break the reliability of GPS. If that goes down, you have to rely on something called dead reckoning, and dead reckoning is based on accelerometers, rotation sensors that measure inertial forces. Dead reckoning was originally developed by sailors as early as the 1600s trying to navigate around the globe. Back then, all they had was a compass, and that gives you a direct direction, but not a position. So how do you work out where you are? Imagine you are a sailor trying to make your way over to America. You start by locating your position on the map by looking for the port you are leaving from. You decide to head to America by moving straight west. If we make the physicist assumption that ocean currents and stray winds don't knock us off course at all, and we follow our compass reading perfectly where we are on the map, is a simple question of how long we've been traveling multiplied by our speed. Sailors determined a ship's speed by a log with a rope tied to it. Overboard every 47 ft a knot was tied in the rope, and by counting how many knots were pulled out by the log, the ship could determine how fast it was moving. This gave us the definition of speed, measured in knots, still used by ships and aircraft to this day. This worked okay for sailors back then, but for some reason never caught on with commercial aircraft pilots, maybe because you need a lot more rope, but also because these systems weren't accurate enough, and velocity is rarely constant. So during the mid-20th century, particularly during World War II, dead reckoning systems moved to measuring acceleration rather than velocity. These worked broadly the same, but measured acceleration over time to calculate velocity, then velocity over time to calculate position. I like to think of this as basically what you do if you ever find yourself kidnapped and put in the back of a trunk. You feel the movements of the car around you and keep track of your position. This process works because every action has an equal and opposite reaction. To understand this better, you might imagine Einstein in a rocket ship in space. As the rocket accelerates, he gets pushed to the bottom of the ship. Similarly, moving left or right causes him to bump into the opposite wall. The device that measures all of these movements is called a inertial measurement unit, or an IMUN. It measures changes in acceleration or deceleration by watching its internal Einstein bump around. But why is this so interesting? It means that unlike GPS, no external reference signal is needed, which could otherwise be vulnerable to hacking, jamming, or poofing. Dead reckoning systems just need to know where they started, and they can use the laws of the universe to determine the rest. They are effectively unhackable, assuming at least that no one has direct access to the device. An elegant solution for keeping track of reality. The problem with normal IMUs is that their sensitivity is limited, and the reason for that is that all of these sensors have an unavoidable level of drift and noise, and that drift and noise accumulates over time. So you start off with your known position, and you integrate forwards your local acceleration and rotation for a few minutes, a few hours, and a few days, and eventually the uncertainty of your position grows and grows and grows until it's no longer usable. So if imagine you're a submarine, you're trying to go from the middle of the ocean through a narrow straits Essachan gap without broadcasting your position. With sonar or any emissive technology, you then are more and more uncertain about your ability to navigate underwater. And I pick underwater because GPS does not penetrate underwater at all. So regardless of the situation, you always need inertial navigation. Underwater, the goal for inflection is to overcome the limitation of traditional inertial measurement systems by developing one based on the quantum properties of the universe and a state of matter called a Bose-Einstein condensate. Because I'm an experimental physicist and I like understanding how things actually work, I wanted to see deep within their system to see how the pieces of this puzzle come together to do that. Though the first challenge is to make some of the coldest atoms in the universe. Can you start by just talking me through how you actually go about cooling an atom using a laser CU? That sounds utterly counterintuitive, you know. Like usually you think of lasers as heating things up. How do you actually use a laser to cool something down? So the basic concept is when the photon of light comes in and interacts with the atom, it sort of stays momentarily with the atom and then is re-emitted into the environment randomly in all directions. And because every time an atom experiences an interaction with the laser light, it loses a little bit of energy. Its kinetic energy is slowly sapped away as it interacts with many photons from the beams. And this happens in a way which opposes motion. So if the atom moves towards the laser beam, it scatters more light than if it's moving away from the laser beam. This phenomena has been known for a while, but I always find it amazing. It's called Doppler cooling, as you might expect from the name. It exploits the Doppler effect, which is the change in frequency or wavelength of any wave perceived by an observer moving relative to the source. You're probably reasonably familiar with this in the example of a car moving towards you. As it moves towards you, its engine sounds like it's at a higher pitch or higher frequency than when it passes you and starts moving away. The same thing happens, though, with light. Atoms are exposed to a laser light that is slightly red-shifted, meaning that its frequency is slightly lower than the natural frequency that the atom wants to absorb. The atom's thermal motion is random in nature as it bumps into other nearby atoms, but when it moves towards the laser light, the Doppler effect causes the light to appear slightly blue, shifted, bringing the light's frequency closer to the atom's natural absorption frequency and making it easier for the atom to absorb the light. Upon absorbing the photon, the atom experiences a recoil in the opposite direction to its motion, slightly reducing its speed. After absorbing the photon, the atom will eventually reach the photon in a random direction. This process is repeated millions of times with the atom absorbing photons from the laser light and losing a little bit more speed in each interaction. If lasers are applied from all 6 directions, this can slow down the atom essentially to a dead stop. Now that will slow the atoms down, but it won't trap them. So what we also add is a magnetic field, and that adds a restoring force, so the atoms are sucked into the center of the magnetic field. In this setup, we have 6 separate laser beams arranged, so one from this direction and its partner from above, one from this direction and its partner, and then one kind of in this direction and one traveling this way. And so this means that we have a laser beam in pushing the atoms in all 3 dimensions and both axes. And this is the first stage of what we will eventually do, which is to trap and cool atoms way colder than that, even to the state of matter, known as Bose-Einstein condensate. This magnetic optical trap, or MOT, means that you can hold on to these super cold atoms in the middle of a vacuum chamber like this and keep them away from the sidewalls of your container so they don't touch it and instantly start to heat up. This is kind of hard to see happening because, well, it's a cloud of atoms, but also the laser is in the infrared, which our eyes and our cameras aren't very good at detecting here. My eyes in our main camera couldn't see anything, but when I put my phone in front of our camera, you can suddenly see a bright red dot. This is the trapped cloud of atoms. That's because the DSLR that we're shooting on had an IR filter over the top of it, meaning that we couldn't see any infrared, but our mobile phones didn't. The team helped make this slightly easier to understand by blocking and unblocking the line of the laser, which you can see on this screen. With a special IR camera, the cloud of ultra-cold atoms spontaneously assembles and then kind of explodes as the trap and confinement is turned off. What's nice here is you can see as the atoms disappear, you can see them flying away because they're no longer held by the force of the trap, and they just expand ballistically into the volume of the vacuum chamber. And yes, this does look like a blurry smud on a screen, but that's quantum physics for you. It almost always looks like that. What was really impressive is how you can then make this atom cloud do something useful for you to understand how this system works, we need to get hands-on with the actual device. Cool, heavy, valuable input be this. Device, to say the least, is reasonably complicated. It's simple as long as you know quantum computing is quantum computing. What we're looking at here is what we call the double mop chamber. Generates a 2DM, so this is similar to a 3DM, but we're confined in two dimensions. It's a line cold atom. We deliberately leave the third dimension free. That's so we can introduce what we call a push beam, so that's another laser. Beam along the axis in that parts, momentum onto the atoms in that axis, and they propagate up into the top chamber here. And so this is then where we do the three-dimensional cooling, and then we can ramp those magnetic fields and the currents in the chip to load atoms into what we call the chip trap. Reason why we want to do that is because we want to generate this the coldest state. His is exactly what we want. We want to prepare Bose-Einstein condensate, and then we want to do atom interferometry with it in order to detect motion with exquisite precision. Interferometry looks at the interpattern between two traveling waves. It is used in experiments you might have heard of before, like LIGO, to detect gravitational waves as they move through the Earth. Usually interferometers interfere waves of light, but here we want to interfere waves of matter. This is kind of wild. I think we're all pretty familiar with light reflecting off of a material surface like a mirror, but it is reasonably rare that we see material reflecting off of a light surface, but that is exactly what is happening here. Here we can see the atoms from above. So the black wires here are how we're going to run current through there, and that's going to create the trap. I'm going to shine a very powerful laser called a dipole laser. From the side, then I'm going to apply a coherent laser pulse, which will split this cloud into two. The atoms are going to move in opposite directions inside the dipole. Then we're going to coherently flip them back so that they recombine in the middle and after, completing this interferometry sequence. The phasor the atoms is sensitive to the acceleration, so we can take an image of the cloud and read out the portion of the cloud in each of the momentous state, and that will be a fingerprint of how the cloud was accelerating during the measurement. That image is destructive, so we will no longer have a B Einstein condensate. The atoms will be warm and they'll be dispersed in the vacuum chamber, and therefore we have to start the whole cycle again, so we get one image every cycle, which is about once a second. So what this technique relies on is that if there are any small changes to acceleration, the ship moving up, down, left, right, forwards, or backwards, this will impart a small difference in the two clouds of atoms such that when they are brought back together and recombined, you see a small interference signal correlating to this acceleration. Don't get me wrong, every single step of this process is incredibly difficult, and it would be an impressive feat if it was demonstrated just in the laboratory alone, but this is already far closer to reality, and back in May the team flew this system on board a research flight to prove about its capability. This is a video that we took in flight. Here you can see the aircraft banking, and on the screen you see a single blob there, and that blob is a Bose-Einstein condensate being produced in this particular video. We're alternating between taking a BC and then just imaging that directly and taking the BC and doing the first round of splitting that you need to do for interferometry. Whether you split or whether you just look at the BC, you drop the atoms, they free fall briefly, and you do what's called absorption imaging, which is very simple. It's looking at the shadow the atoms create, and by looking at the relative density of these three blobs, you know the relative proportion of atoms in each of the three superposition states, and then you can back calculate what phase you would have accumulated, obviously due to an acceleration or rotation. The fact that you can even brag split a BC in a plane and it's stable is remarkable. It's really, really amazing. And you can do so while the aircraft moving around. You can see the cloud moving in the background to add some context as to why this is so impressive. The enemy of all quantum engineering is noise, both mechanical and electromagnetic. It's what we are fighting when we're building a quantum computer that makes it so hard to get, right? And what the team here is having to overcome, you come from a physics lab where everything is bolted onto FL floating optical tables, and the magnetic and the light environment and everything else is quite well shielded to taking this on a really dynamically challenging environment. like an aircraft where the aircraft is shaking violently because of the engines. There is a 6, whatever, gigs weather radar at the front of the thing blasting this air traffic control. It's a very challenging environment we are finally getting to. The point where quantum is becoming robust. The learnings that are here will map directly to other quantum technologies and open up applications that we never thought possible. The challenges now is to show the performance and the capabilities of the quantum senses in more of the deployed trials and benchmark that against existing technologies and try to rapidly ascend that technology development curve. So lots of the existing technologies I mentioned before are plateauing in their performance. We're not going to get a 10x or 100x improvement in fiber optic gyros or ring laser gyros in the next few years. They've been very well engineered by lots of very smart people, but they're coming to the end of their development trajectory. We're just at the start of the development trajectory for quantum technologies at the first generation of our products will be something that's rack-mounted system, something that can go into a data center or onto a ship or an aircraft, but ultimately where we're going longer term, and when I say longer term, this is over. The next few years is to ruggedize and miniaturize the systems using, for example, photonic integrated circuits. So taking the lasers and the optics and the vapor cells that you've seen and printing these on silicon so that ultimately these products will be something that could fit in the palm of your hand, but positioning isn't the only problem that these systems could tackle. So because the atoms are sensitive to acceleration, they are by the same exact principle sensitive to gravity. And so if we can measure gravity with exquisite precision, it enables us to, for example, understand where there are mineral deposits under the earth. We can measure tunnels. We can measure geologic formations. One day it may have applications from helping guide autonomous vehicles around high-rise cities or helping us to navigate space. But first it will be set to work to protect flights around the world, which, as of 2024, 900 flights a day on average, are now encountering GPS spoofing, technology made possible by some of the most complicated but fundamental laws of our universe. Diving into these sorts of technologies is literally the coolest thing about what it is that I get to do. As a factor of being on YouTube, if you like this video, I'm going to leave some more kind of behind-the-scenes footage over on Patreon and post it here for channel members. Please do consider supporting us by joining or just by leaving a like or leaving a comment. Let me know what other technologies you. People say they understand gravity. They say it confidently, casually, as if saying the word itself solves the mystery. But the truth is uncomfortable. Most people don't understand gravity at all. They recognize its effects and mistake that for understanding. When you drop an object and it falls, you haven't explained gravity. You've just noticed it happening. The moment you say, objects fall because gravity pulls them, you've done something sneaky. You've replaced a mystery with a word and pretended the mystery is gone. It isn't. Ask a simple question. What does pull actually mean here? Where is the pulling happening? Through what mechanism? At what moment does space decide now you fall? Most explanations collapse right there. People like to imagine gravity as a force reaching out across empty space, grabbing things like invisible hands. That picture feels satisfying, and it's wrong. Nature does not operate to satisfy human imagination. What actually happens is stranger. Objects are not being dragged through space. They are following the shape of space itself. And that sentence should make you uncomfortable because it doesn't behave like anything in daily life. Space is not a stage where things happen. Space is part of what happens. And here's where people really get lost. Using mathematical formulas doesn't automatically mean understanding. A formula can predict behavior perfectly and still tell you nothing about why reality behaves that way. We can calculate gravity with stunning accuracy. We can send spacecraft across the solar system using it. But if you ask, why does mass affect space at all? The honest answer is, we don't know. And that's not weakness, that's intellectual integrity. The universe doesn't owe us explanations that fit inside our intuition. Our brains evolved to throw rocks and avoid predators, not to understand the structure of space-time. So when someone tells you they fully understand gravity, be careful. They may understand how to use it, not what it is. Real understanding begins when you're willing to say, I can describe what happens with incredible precision, but the deeper reason remains mysterious. That humility is not ignorance. It's the starting point of real science. Gravity isn't simple, and pretending it is, that's what everyone gets wrong. People say gravity is a force. That single sentence has done more damage to understanding than almost anything else in science. It sounds harmless, sensible, even educated, but it quietly sneaks in a picture that doesn't belong there, a picture of something reaching across empty space and pulling on objects like an invisible rope. Once that image settles in your mind, real understanding becomes almost impossible, because nothing in nature behaves that way. When you say force, you're borrowing from everyday experience. A hand pushes a door, a magnet pulls a piece of iron. You can point to where the force comes from, how it's applied, and what changes when you remove it. Gravity doesn't fit that pattern, and pretending that it does is where the confusion begins. Drop a stone, it falls. So you say gravity pulled it. But that statement explains nothing. It just repeats the observation using a word that feels explanatory. If I ask how the stone knows which way to fall, or why it accelerates instead of moving at a constant speed, or where the pulling is coming from, the answers suddenly become vague. That's not understanding, that's vocabulary hiding ignorance. What's actually happening is far stranger than a pull. The stone is not being yanked downward by some cosmic hand. It is moving exactly as it would if nothing were acting on it at all. That idea sounds absurd until you realize the mistake. You've been assuming space is passive. It isn't. Space is part of the physical system, and it has structure. Imagine removing gravity entirely, not just the force, but the concept, as people usually imagine it. What remains is an object moving nadir, ally following the geometry of the space it exists in. The motion feels forced only because the geometry isn't what your intuition expects. Your intuition wants straight lines. Nature doesn't care. Mass changes the structure of space and time in its vicinity, not metaphorically, not poetically, physically. Objects nearby aren't pulled, they are guided. They move along the paths that space itself makes available to them. The stone falls because that is the straightest possible path in a curved environment. This is where most people stop listening. Not because it's wrong, but because it refuses to match common sense. Common sense evolved to survive at human scales. It works for throwing balls and stacking boxes. It breaks completely when you apply it to the universe. Gravity doesn't feel intuitive because intuition was never meant to handle it. Calling gravity a force makes you feel like you've tamed it, like you've put a wild idea into a familiar box. But all you've really done is trade accuracy for comfort. And comfort is the enemy of understanding. You can calculate gravitational effects with incredible precision. You can predict orbits, tides, and the bending of light. You can build technologies that rely on those predictions. None of that requires you to imagine a pulling force. The mathematics works because it respects the structure of reality, not because it agrees with human intuition. Here's the uncomfortable part. Even with all that math, we still don't know why mass affects space at all. We can describe how it does. We can measure it. We can test it. But the deeper reason remains hidden. And pretending gravity is just another force delays that realization. Real knowledge doesn't begin with confident answers. It begins when you notice that your explanations are too simple. When people insist gravity is a force, they're often defending a mental shortcut. It's easier to picture a pull than to accept that space itself can have shape, that time can slow down, that motion can be natural without being driven. But the universe is under no obligation to be easy to picture. The mistake isn't in using the word force casually. The mistake is believing that the word captures what's really going on. Gravity is not a thing reaching out and acting on objects. It is a relationship between mass, space, and motion. Once you see that, the falling stone stops being a mystery disguised as an answer. It becomes a clue, a hint that the universe is structured in a way that no everyday analogy can fully capture. And that realization matters more than any formula. Because the moment you stop demanding that reality behave like your intuition, you finally give yourself a chance to understand it. Saying that something happens is not the same as explaining why it happens, and confusing the two is one of the oldest mistakes people make when talking about gravity. When an object falls, everyone agrees on what they saw. The disagreement begins the moment someone claims they've explained it. The explanation usually sounds confident. Mass attracts mass. Gravity pulls things downward. Objects fall because of a force. Each sentence feels complete. Each sentence gives the listener the false comfort of understanding. And none of them answer the actual question. Describing an effect is easy. You point, you label, you repeat what your eyes already told you. Explaining something means uncovering the mechanism that makes the effect unavoidable. Gravity is where people stop at the description and pretend the job is finished. If I tell you that a clock stops because the batteries are dead, I've explained something. If I tell you it stopped because it stopped ticking, I've said nothing. Yet that's exactly how most gravity explanations work. Objects fall because gravity pulls them. Gravity pulls because objects fall. The reasoning loops back on itself, sounding technical but going nowhere. This confusion survives because the descriptions are accurate. Objects really do fall. Planets really do orbit. Light really does bend near massive objects. But accuracy is not the same as understanding. A weather report can describe a storm perfectly without explaining the physics that caused it. People assume that adding a scientific word turns a description into an explanation. It doesn't. A word is just a label. The moment you stop questioning the label, you stop learning. Ask a simple follow-up question. How does gravity do what it does? Not what happens, but how it happens. At that point, most explanations begin to unravel. The language becomes vague, the gestures become larger, analogies replace mechanisms. That's not failure, it's exposure. It reveals where understanding ends and memorization begins. The universe does not run on summaries. The real explanation of gravity doesn't start with falling objects. It starts with the structure of space and time. It starts by abandoning the idea that space is an empty container where things move independently. Space is not passive. Time is not universal. Motion is not absolute. None of these statements come from observing an apple fall. They come from asking why it must fall the way it does. Once you see that, the falling object stops being the explanation and becomes the evidence. The orbiting planet is not the cause of gravity. It is a consequence. Descriptions point outward. Explanations point inward. This difference matters because descriptions don't scale. They work only where you've already seen the effect. Explanations let you predict new behavior. They tell you what will happen in situations no one has observed yet. Gravity only became useful as a scientific concept when it stopped being a list of behaviors and became a structure that could be applied universally. There is also a psychological trap here. Descriptions feel satisfying because they align with intuition. You already believe objects fall, so hearing it stated confidently feels like confirmation. Explanations often feel unsettling because they replace familiar pictures with abstract relationships. The brain resists that discomfort and clings to the story it already knows. That resistance is the enemy of progress. When someone says they understand gravity because they know what it does, they're mistaking recognition for insight. You can recognize a face without knowing anything about the person's thoughts. Gravity is no different. Observing its behavior tells you almost nothing about its nature, and here's the part people don't like admitting. Even the best explanations we have are incomplete. We can describe the structure of space-time with astonishing precision. We can predict gravitational effects with numbers that agree with experiments to absurd accuracy. But when you ask why space-time has this structure in the first place, the answer runs out. That's not a flaw of science, that's honesty. Confusing description with explanation creates arrogance. It makes people think the problem is solved when it isn't. It shuts down curiosity and replaces it with repetition. Real understanding stays alert to the gap between what we see and why it must be that way. Gravity forces that humility on us. It reminds us that naming a phenomenon does not tame it. Listing its effects does not reveal its cause. Understanding begins only when we stop being satisfied with what happens and insist on knowing how reality makes it inevitable. And the moment you see that difference clearly, gravity stops being a familiar idea and becomes what it truly is, one of the deepest questions we've ever asked about the universe. The easiest way to hide that you don't understand something is to learn the right words and use them confidently. Most people don't realize they're doing it. They think speaking fluently means thinking clearly. But fluency and understanding are not the same thing. Words can become a shield, a way to stop questions instead of answering them. Gravity is a perfect example. Say force, attract, ion, curvature, or field, and people relax. The vocabulary signals competence. The conversation ends. No one asks what those words actually mean because the words sound like meaning. But a word is not an explanation, it is a placeholder. It marks the spot where understanding is supposed to go. The danger begins when the placeholder is mistaken for the thing itself. When someone says mass attracts mass, it feels like knowledge. Yet nothing has been explained. The word attracts carries emotional weight from everyday life. Magnets, hands pulling objects closer. But gravity does not behave like those things. The word borrows clarity from unrelated experiences and smuggles it into a context where it doesn't belong. This is how ignorance survives among intelligent people. You can memorize definitions, recite equations, and repeat accepted phrases while understanding almost nothing about the underlying reality. The words become a performance. They create the illusion of mastery, especially to others who share the same vocabulary and the same blind spots. Real understanding is quieter. It hesitates. It asks uncomfortable questions. It is willing to say, I don't know what that word actually refers to. Most people avoid that moment because it feels like failure. In reality, it's the only honest place to start. Language evolved to help us coordinate actions, not to reveal the structure of the universe. It works beautifully for everyday life and badly for fundamental physics. When we forget that limitation, we confuse linguistic convenience with truth. Take any popular explanation of gravity and strip away the technical terms. What remains is often nothing more than a description of motion. Objects fall, planets orbit, light bends. The words decorate the observation but don't penetrate it. That decoration is seductive. It lets us feel informed without being challenged. It replaces curiosity with confidence, and confidence, when it isn't earned, blocks learning. The real test of understanding is simple and brutal. Can you explain the idea without relying on the word itself? If you remove the term gravity and nothing meaningful remains, you never understood gravity. You only learned when to say the word. This is not a criticism of learning terminology. Technical language is necessary, but it is dangerous when treated as the destination instead of the tool. Words should point beyond themselves. When they don't, they become intellectual furniture, impressive, heavy, and useless. Science advances by refusing to let words settle into complacency. Every serious idea is constantly pressured. What does this term refer to? What observation forces us to use it? What would happen if it were wrong? When that pressure disappears, science turns into ritual. Gravity exposes this weakness because it resists everyday imagery. The more you lean on familiar language, the more misleading it becomes. You can say space curves, but what does curvature mean without embedding surfaces in higher dimensions? You can say time slows, but compared to what? Each phrase opens a door and immediately pretends it has answered the question. That's not dishonesty. It's a limitation. The mistake is forgetting it's a limitation. True knowledge doesn't hide behind words. It uses them carefully, temporarily, and with awareness of their flaws. It treats every term as a question mark, not a conclusion. This is why the most dangerous sentence in any intellectual discussion is, everyone knows what that means. That sentence marks the exact moment thinking stops. Understanding begins when words fail, when explanations become awkward, when you feel the gap between what you can say and what is actually happening. That discomfort is not a sign of ignorance. It's evidence that you're finally approaching something real. Gravity doesn't become clearer as vocabulary grows more polished. It becomes clearer when you stop mistaking polished language for insight. Words are too. When they stop revealing and start concealing, the honest response is not to speak louder, but to think harder. The universe does not care what feels reasonable to you. That may be the most important thing to understand before trying to understand gravity, because almost every mistake people make begins with the same assumption, that reality should behave in a way that matches human intuition. It won't. It never has. Intuition is a survival tool. It evolved to help us judge distance, speed, weight, and danger at human scales. It is excellent for crossing streets and throwing stones. It is completely unreliable when applied to the structure of the universe. Yet we keep trusting it. We expect causes to be local. We expect time to tick the same for everyone. We expect space to sit quietly in the background while objects move through it. These expectations feel obvious because they work in everyday life. Gravity violates all of them, and intuition fights back by trying to force it into familiar patterns. That's why people insist on imagining gravity as a pull. Pulling is something we understand. Curved space is not. So the mind chooses the comfortable picture and ignores the consequences. Nature does not negotiate with comfort. When experiments contradict intuition, the experiment wins. Always. Reality does not adjust itself to match the way humans prefer to think. It behaves the way it behaves, and our job is to adapt our thinking to it, not the other way around. This is why gravity feels strange even after years of exposure. Nothing in ordinary experience prepares you for a universe where straight lines bend, clocks tick at different rates depending on motion and position, and falling can be the natural state of motion rather than a response to a force. The resistance to these ideas isn't intellectual, it's psychological. The brain is wired to expect stability and simplicity. Gravity offers neither. It demands that you abandon the idea of absolute time and fixed space, concepts that feel as solid as the ground beneath your feet. That ground, incidentally, is not holding you up because of a force pulling you down. It's preventing you from following your natural path through space-time. Intuition hates that sentence. Reality doesn't care. Every major advance in understanding gravity required ignoring what felt obvious. The motion of planets does not follow perfect circles, no matter how aesthetically pleasing circles may be. Light does not travel in straight lines near massive objects, no matter how deeply straight lines are embedded in human reasoning. Time does not flow uniformly, no matter how desperately intuition demands it. These facts are not philosophical, they are measurable. You can build instruments that detect them. You can run technologies that fail if you ignore them. Intuition can complain all at once. The universe remains unmoved. The problem arises when people treat intuition as evidence. When something feels wrong, they assume it must be wrong. That instinct is useful in daily life and disastrous in science. Gravity teaches this lesson relentlessly. The more intuitive an explanation feels, the more likely it is to be misleading. Understanding requires discipline. It requires the willingness to hold an idea that feels wrong because the evidence demands it. That is not a natural human skill. It has to be trained. This is why genuine comprehension often feels fragile. You're constantly aware that your mental pictures are approximations, metaphors, scaffolding that may collapse under better data. That discomfort is not a flaw. It's the price of accuracy. The universe does not reward belief. It responds only to interaction. You can deny gravity's implications, misunderstand them, or find them ugly, and your GPS system will still fail if you ignore relativistic effects. Nature enforces its rules without explanation or apology. The lesson is not to abandon intuition entirely, it's to recognize its limits. Intuity. On is a guide at familiar scales and a liar at fundamental ones. Gravity lives at those deeper levels, where comfort must be sacrificed for truth. The moment you stop demanding that reality makes sense to your instincts, you gain the freedom to actually understand it. Nature does not care how you think it should behave. It only cares how it does. And that indifference is exactly what makes it worth studying. The moment you think a formula is the answer, you've stopped asking the most important question. Formulas are powerful. They predict outcomes with astonishing accuracy. They let us calculate trajectories, energies, and motions with confidence that borders on arrogance. And that success hides a dangerous misunderstanding. Prediction is not explanation. A formula tells you what will happen if certain conditions are met. It does not tell you why the universe obeys that rule in the first place. When people confuse those two, science turns into bookkeeping. Gravity is often presented as solved because the math works. The equations agree with observation to an almost absurd degree of precision. Satellites stay in orbit. Time corrections keep navigation systems functioning. The numbers never lie. But numbers are not reasons. You can write down a perfect formula and still have no idea what reality is doing underneath it. The equation does not cause gravity. The equation describes a pattern we have noticed. It compresses behavior into symbols and relationships. That compression is useful, but it is not understanding in the deepest sense. The universe is not consulting our mathematics before it acts. This distinction is uncomfortable because formulas feel final. They carry authority. They end arguments. When someone writes symbols on a board, the conversation stops. But stopping the conversation is not the same as finishing the inquiry. Gravity forces this humility because even our best equations leave questions untouched. We can describe how mass influences the structure of space and time. We can calculate the resulting motion of objects within that structure. But when you ask why mass has that influence at all, the trail ends. Not with an answer, with silence. That silence is not failure. It is information. It tells us where knowledge ends and mystery begins. Pretending otherwise replaces curiosity with complacency. There is a temptation to treat science like a ladder. Climb high enough and you reach certainty. Reality is messier. Each advance replaces old questions with deeper ones. The better the formulas become, the more sharply the limits stand out. Gravity is not mysterious because it is poorly understood. It is mysterious because it is understood well enough to expose what we do not know. The math works because the universe behaves consistently. That consistency is astonishing. It does not need to exist. The fact that reality can be captured by mathematical relationships at all is one of the deepest puzzles we face. Writing the formula down does not solve that puzzle. It highlights it. People often want explanations that feel mechanical, gears turning, forces pushing, causes acting locally. Gravity refuses to cooperate. It replaces mechanisms with geometry, action with structure, force with relation. The equations express that shift, but they do not justify it. This is where intellectual honesty matters. You can either pretend the formula is the explanation, or you can admit that it is a map, not the territory. Maps are invaluable. They are not the landscape. Real understanding requires living with that distinction. It requires accepting that some of the most successful ideas in science are also the most incomplete. The power of a theory is not measured by how comfortable it feels, but by how much reality it captures without lying about what remains unknown. The danger of overconfidence is subtle. When people believe the formula is the truth, they stop looking for deeper structure. They confuse effectiveness with completeness. History shows how fragile that assumption is. Every time we thought the equations were final, nature disagreed. Gravity will likely do the same again. The correct response to a powerful formula is not reverence but curiosity, not silence but sharper questions. The equation should not close the book, it should open it wider. Understanding does not mean eliminating mystery, it means knowing exactly where the mystery begins. Gravity teaches this lesson brutally and beautifully. We can predict it, we can use it, we can rely on it. And still, when we ask why the universe is built this way rather than another, the formula has nothing to say. That is not a weakness of science, it is its strength. Because the moment you accept that the real mystery lies beyond the symbols, you stop mistaking answers for understanding, and you start doing the kind of thinking that actually moves knowledge forward. Imagine someone stands up and says, I have calculated a planet with a 99.7% chance of life. Your first reaction should not be excitement. Your first reaction should be suspicion, because numbers don't make something true. Methods do. A percentage without an explanation is not science, it's decoration. To say life exists somewhere is easy. To prove it is brutally hard. You must ask, what do you mean by life? Chemistry, metabolism, reproduction, error correction? If you don't define the terms, you are not discovering, you are guessing. The universe is not impressed by our confidence. It doesn't reward hope. It only responds to experiments that can fail. If your idea cannot be proven wrong, it is not science. It is belief wearing a lab coat. Now consider this. The same equations that suggest life is common can also show how fragile it is. One missing molecule, one unstable orbit, one star that flares too often, and your beautiful probability collapses to zero. This is why real thinkers fall in love not with answers, but with questions that hurt. The goal is not to be right. The goal is to not fool yourself, because you are the easiest person to fool. So if someone claims a planet with a 99.7% chance of life, the correct response is not applause. It is curiosity sharpened into a knife. Show me the assumptions. Show me what would prove you wrong. Show me the experiment. Because the moment we stop questioning our most exciting ideas, we stop doing science and start telling comforting stories to ourselves in the dark. And the universe does not reveal its secrets to storytellers. It reveals them to those brave enough to doubt even their best ideas. The original idea was weak because it relied on a false claim. This version is strong because it teaches people how to think, not what to believe. Extraordinary claims are cheap. Evidence is expensive. Anyone can announce a discovery. Anyone can attach a dramatic number to an idea and demand attention. But the universe does not care about our announcements. It does not reward confidence, volume, or popularity. It only responds to work that survives contact with reality. When someone says there is a 99.7% chance of life, the sentence sounds powerful, but power is not the same as truth. Numbers feel authoritative because they look precise, yet precision without foundation is theater. A percentage is meaningless, unless you can trace every step that produced it and show where it could collapse. Otherwise, it is not a result. It is a performance. Real understanding begins with discomfort. You must ask what assumptions were smuggled in before the calculation even started, what definition of life was chosen, and more importantly, which definitions were quietly ignored. Is life reduced to chemistry, to replication, to information processing, or to something we have not yet imagined? Each choice narrows the conclusion, and each narrowing hides uncertainty. Ignoring this does not make an idea stronger, it makes it fragile. Nature is ruthless. It does not bend to elegant theories or beautiful equations. A planet can sit in the so-called perfect zone and still be dead. A single unstable orbit, a violent star, a missing chemical pathway, and all probabilities collapse to zero. This is not pessimism, it is respect for complexity. The universe is not obliged to cooperate with our expectations. The most dangerous moment in thinking is when an idea feels complete. That sense of closure is seductive because it promises certainty, and certainty feels like control. But science does not advance by protecting ideas. It advances by attacking them. The strongest ideas are those that invite assault because they have something solid to defend themselves with. If a claim cannot clearly state how it could be proven wrong, it is not a scientific claim. It is a belief disguised as intelligence. The requirement is simple but unforgiving. Show the experiment that LD embarrass you if the result went the other way. Without that, you are not searching for truth. You are searching for confirmation. We like to imagine discovery as a dramatic moment, a flash of insight that suddenly reveals how things really are. In reality, discovery is mostly failure. It is the slow elimination of ideas that almost worked. Every wrong turn teaches us where not to look. Every negative result sharpens the question. Progress is not made by bold claims, but by careful rejection of attractive mistakes. This is why skepticism is not cynicism. Skepticism is a form of respect for reality as it is, not as we wish it to be. To question a claim is not to attack the person who made it. It is to take the claim seriously enough to test it. Flimsy ideas need protection. Strong ideas demand opposition. The real enemy of understanding is not ignorance. Ignorance can be cured. The enemy is the illusion of knowledge, the feeling that we know more than we actually do. Once that illusion sets in, curiosity dies. Questions feel unnecessary. Doubt feels like weakness. And thinking stops. A mind trained to chase evidence learns humility. It learns that being wrong is not a failure but a correction. Every time reality disagrees with us, we gain something more valuable than pride. Alignment with the way the world actually works. That alignment is rare, fragile, and worth defending. So when you hear an extraordinary claim, resist the urge to be impressed. Be curious instead. Ask what had to be assumed for the claim to survive. Ask what observation would destroy it. Ask how much is truly known and how much is being guessed with confidence. Because in the end, the universe does not yield its secrets to those who speak the loudest or calculate the flashiest numbers. It yields to those who are patient enough to doubt, disciplined enough to test, and honest enough to admit when an idea, no matter how exciting, turns out to be wrong. Extraordinary claims are cheap, evidence is expensive, and truth is paid for in full or not at all. Probability without method is just a fancy guess. It sounds scientific, it looks precise, and it carries the authority of mathematics, but without a clear path that leads to it, a probability is nothing more than confidence dressed up as rigor. The danger is not that such guesses exist, but that we forget they are guesses and start treating them as conclusions. A number feels safe, it feels controlled. Saying maybe sounds weak, but saying there is a 92.4% chance feels responsible, even if no one can explain where that number came from. The human mind is easily impressed by precision, yet nature is not. Nature does not respond to decimals, it responds to mechanisms. If you cannot show the machinery behind the number has no authority. Method is what turns curiosity into knowledge. It forces you to define what you are measuring, what you are ignoring, and why. Without method, probability floats freely, disconnected from reality. You can assign a percentage to almost anything if you are willing to hide uncertainty inside assumptions. The more assumptions you hide, the cleaner the final number looks, and the more misleading it becomes. Consider how easily probability can be abused. Change the definition of success, and the likelihood shifts. Remove inconvenient variables and confidence rises. Assume independence when none exists, and suddenly the universe looks predictable. These are not small errors, they are structural failures. They do not slightly weaken a conclusion, they invalidate it. Real methods are uncomfortable because they expose ignorance. They force you to admit what you do not know and quantify how much it matters. They make uncertainty visible instead of burying it. A good method does not guarantee a dramatic result, it guarantees an honest one. That honesty often leads to messy conclusions, wide error bars, and probabilities that refuse to be impressive. This is why serious thinking avoids premature numbers. Before asking how likely, you must ask based on what? What evidence exists? How was it measured? How reliable is it? What alternative explanations remain? A probability that cannot answer these questions is not an answer at all. It is an illusion of progress. The discipline of method also protects us from ourselves. We are not neutral observers. We want certain outcomes to be true, and that desire quietly shapes our calculations. We notice evidence that supports us and overlook what challenges us. A method, properly designed, is a defense against this bias. It is a way of saying, I do not trust my intuition, so I will build a system that corrects it. Without that discipline, probability becomes a storytelling device. It reassures, persuades, and impresses, but it does not explain. It replaces understanding with comfort. The problem is not that the story is false. The problem is that it cannot be checked. And what cannot be checked cannot be improved. Science advances not by guessing better, but by testing harder. A probability earns respect only when it survives attempts to break it. When new data arrives, the number must be allowed to change or die. If it is protected from revision, it is no longer a probability. It is a belief. The most reliable thinkers are those who treat every number as provisional. They see probability not as a verdict, but as a temporary summary of incomplete knowledge. It is a snapshot, not a destination. The moment you forget this, you stop learning. In the end, probability is a powerful tool, but only when anchored to method. Without that anchor, it drifts, convincing and useless at the same time. It gives the feeling of understanding without the substance, and feeling informed is far more dangerous than knowing you are ignorant. So be wary of clean percentages and confident predictions. Ask how the number was built, what assumptions hold it up, and what would cause it to collapse. Because until a probability is earned through method, it is not insight, it is just a fancy guess, and the universe has never been fooled by those. Nature doesn't care what we want to be true. It does not negotiate with our hopes, our fears, or our favorite ideas. It does not adjust its behavior to match our expectations or reward us for how much we believe in something. Reality operates by its own rules, and those rules remain unchanged whether we understand them or not. This indifference is uncomfortable because it strips us of a comforting illusion that desire has any influence over truth. We want the universe to be simple, meaningful, and aligned with our intuition. But wanting does nothing. A bridge collapses if the calculations are wrong, no matter how strongly the engineer believes in it. A disease progresses if the treatment fails, regardless of optimism. The world does not respond to sincerity, it responds to correctness. Most errors in thinking are born from emotional attachment. We fall in love with explanations because they feel elegant or satisfying. Once attached, we begin protecting them. We explain away contradictions. We ignore inconvenient facts. We reinterpret evidence so it fits the story we already prefer. This is not stupidity. It is human nature. But human nature is precisely what disciplined thinking must guard against. Reality has a way of humiliating unchecked confidence. An idea can survive endless discussion and still collapse the moment it meets an experiment. Words are cheap. Nature is expensive. It charges full price for every misunderstanding. When a theory fails, it does not fail gently. It fails completely without apology. This is why evidence matters more than intention. You can be honest, intelligent, and deeply committed and still be wrong. Truth is not awarded for effort. It is discovered through confrontation with facts that do not care about your feelings. The sooner this is accepted, the faster learning begins. The most dangerous phrase in intellectual life is, "It must be true." That phrase signals that desire has replaced verification. The moment you feel that something has to be correct, you stop testing it. You start defending it. And the defense of an idea is the end of its growth. Progress depends on the willingness to be disappointed. Each time reality refuses to match our expectations, we are given an opportunity to correct our understanding. This requires humility, because it means admitting that our mental picture of the world was flawed. But humility is not weakness, it is accuracy in the face of complexity. Nature's indifference is not cruelty, it is clarity. Because the rules do not change, we can learn them. Because the universe does not lie, our mistakes are exposed. Every failed prediction narrows the range of what might be true. Every experiment that disagrees with theory teaches more than one that agrees. The goal, then, is not to protect ideas we like, but to test them until they either earn survival or collapse. An idea that survives this process becomes reliable. An idea that cannot survive does not deserve loyalty, no matter how attractive it once was. This mindset transforms curiosity into discipline. You stop asking what you hope is true and start asking what the evidence allows. You trade comfort for clarity. And while clarity can be unsettling, it is the only path to real understanding. In the end, the universe offers no guarantees, no reassurance, and no shortcuts. It offers only consistency. Those who accept that indifference, who stop demanding that reality agree with them, gain something rare, the ability to see the world as it is, not as they wish it to be. Nature doesn't care what we want to be true, and that is precisely why, if we are honest and patient enough, it can teach us everything we need to know. Real science survives being questioned. Lies don't. This single fact separates understanding from illusion. Anything that collapses under scrutiny was never knowledge to begin with. It was a fragile construction protected by silence. Truth does not fear inspection. It invites it. Questioning is not an attack on science. It is the engine that drives it forward. Every serious idea is born with the expectation that it will be challenged. Measurements will be repeated. Assumptions will be exposed. Conclusions will be pushed until they either hold or break. If an idea cannot survive this process, it does not deserve to survive at all. Lies depend on obedience. They require agreement, authority, and the absence of doubt. The moment someone asks the wrong question, the structure begins to crack. This is why false ideas are often surrounded by intimidation, certainty, and emotional pressure. They replace evidence with confidence and criticism with hostility. Their weakness is not intellectual, it is structural. Real knowledge behaves differently. It remains intact when challenged because it is built from independent pieces that support one another. Remove one assumption, and the conclusion may weaken, but it does not vanish. Test it from another angle, and the result remains consistent. This resilience is not accidental. It is the product of methodical skepticism applied over time. The act of questioning does something deeper than error correction. It reveals hidden assumptions, the silent premises we forget we are relying on. Many ideas sound convincing only because their assumptions are never spoken aloud. Once exposed, those assumptions can be tested, refined, or discarded. This process is not destructive, it is clarifying. A culture that discourages questions is a culture afraid of discovery. When doubt is treated as disloyalty, knowledge stagnates. Progress requires an environment where asking, "How do you know?" is not an insult but a responsibility. Without that pressure, even intelligent people can convince themselves of nonsense. The strength of science lies in its willingness to embarrass itself. Failed predictions are published. Incorrect models are replaced. No reputation is sacred. This openness is not chaos, it is quality control. Each public failure removes a piece of error from the system, leaving it more accurate than before. Lies, on the other hand, must remain static. They cannot adapt because adaptation would expose contradiction. They resist revision because revision admits fallibility. As new evidence appears, lies multiply explanations to protect the original claim, creating complexity without understanding. This is how deception reveals itself, not by simplicity, but by defensive elaboration. Questioning also protects us from authority. Credentials, status, and confidence are not evidence. They can guide attention, but they cannot replace proof. A statement does not become true because it is spoken by someone respected. It becomes true only if it matches reality. Science institutionalizes this humility by separating the claim from the claimant. The habit of questioning is uncomfortable because it destabilizes certainty. It forces us to live with provisional conclusions and incomplete answers. But certainty gained without challenge is worthless. It feels strong, but it shatters on contact with reality. Uncertainty tested by evidence grows stronger with time. In the long run, the ideas that matter are those that remain standing after repeated attempts to tear them down. They do not survive because they are protected, but because they are correct enough to endure. Everything else fades. No matter how loudly it was once defended, real science survives being questioned. Lies don't. And in a world crowded with confident claims, the courage to question is not cynicism. It is the only reliable path to truth. Curiosity is powerful only when disciplined by doubt. On its own, curiosity is just motion, restless, energetic, and directionless. It drives us to ask questions, but it does not tell us which questions matter or which answers can be trusted. Without doubt, curiosity becomes naive enthusiasm, easily impressed and easily misled. Doubt is not the enemy of wonder, it is its guardian. It forces curiosity to slow down, to check its footing, to ask not only what if, but also how do we know. This restraint does not weaken curiosity, it sharpens it. A question tested by doubt becomes precise. An idea filtered through skepticism becomes meaningful. Unrestrained curiosity accepts stories too quickly. It mistakes novelty for insight and complexity for depth. It is drawn to explanations that feel exciting rather than those that are reliable. Doubt interrupts this pattern. It demands clarity. It insists that explanations earn belief instead of receiving it as a gift. The most valuable questions are not the loudest ones, but the most careful. They expose assumptions, challenge shortcuts, and refuse easy conclusions. Doubt teaches curiosity patience, the patience to wait for evidence, to tolerate uncertainty, and to abandon ideas that do not survive testing. There is a common misunderstanding that doubt kills creativity. In reality, it protects creativity from self-deception. When every idea is accepted without resistance, none of them improve. Resistance is what forces refinement. Doubt applies pressure, and pressure reveals structure. A curious mind without doubt will chase patterns that are not there. It will connect unrelated events and mistake coincidence for meaning. Doubt acts as a filter, separating signal from noise. It asks whether an observation is repeatable, whether an explanation predicts anything, whether it can be wrong. These questions prevent curiosity from drifting into fantasy. Discipline does not mean cynicism. It does not mean refusing to believe anything. It means believing carefully. Doubt does not say this is false. It says this is unproven. That distinction matters. It keeps the mind open without letting it become careless when curiosity and doubt work. Together, learning accelerates. Curiosity explores possibilities. Doubt evaluates them. One expands the space of ideas, the other contracts it toward what is reliable. This balance is how understanding grows, not explosively but steadily. The absence of doubt produces confidence without foundation. Ideas feel complete too early, questions stop, progress stalls. Doubt reopens the process by reminding us that understanding is provisional. Every answer is a temporary resting point, not a final destination. The world is complex enough to punish careless thinking. Patterns emerge, but they are subtle. Causes exist, but they are often hidden. To navigate this complexity, curiosity must be trained. Doubt is that training. It teaches humility, the recognition that the universe is under no obligation to make sense to us immediately. In the end, curiosity alone can entertain, inspire, and distract. But only curiosity disciplined by doubt can discover. That discipline transforms wonder into knowledge and questions into insight. Curiosity is powerful only when disciplined by doubt. Because without doubt, curiosity does not seek truth, it seeks satisfaction.